Hello everybody. In this video we are going to be looking at the solutions to the college prep speed of sound practice problems 1. Let's take a look at problem number 1. A sound wave has a wavelength of 0.75 meters and a frequency of 425 hertz. What is the air temperature in degrees Celsius? We are given the wavelength of the sound wave, which is 0.75 meters. We are given the frequency of the sound wave of 425 hertz, and we are being asked to find the temperature in degrees Celsius. In order to find the temperature, we know that we're going to need to know how fast the wave is traveling, but we are not given the wave speed. We are, however, given the frequency and the wavelength, and from those two, we can find the wave speed. So to find the speed of the wave from the frequency and the wavelength, I simply have to multiply the frequency and the wavelength together. So 0.75 meters times 425 hertz will give me a wave speed of 318.75 meters per second. Now I can use my speed of sound in air formula. So velocity equals 331 meters per second times the square root of the temperature divided by 273 Kelvin. And remember that this temperature always has to be in Kelvin, or it will give me the temperature in Kelvin. I cannot have Celsius temperatures in this formula. So if I rearrange for temperature, I will have the temperature is going to equal 273 Kelvin times V squared divided by 331 meters per second squared. Again, in order to solve for the temperature, I have to square everything because it's inside the radical. So I have to square the velocity. I have to square this temperature, which remember this 331 meters per second is the speed of sound waves at 0 degrees Celsius. And then my radical simply goes away. So when I do all of that out, I am going to have a temperature of 253 Kelvin. Now, in order to convert from Kelvin to degrees Celsius, because I want my final answer to be in degrees Celsius, it's a simple operation. I simply take my Kelvin temperature, subtract 273 Kelvin from that. So 253 Kelvin minus 273 Kelvin will give me an air temperature of negative 20 degrees Celsius. Problem number 2. The sound a mosquito makes is produced when it beats its wings at the average frequency of 620 wing beats per second. What is the wavelength of the sound waves produced by the mosquito? Assume that the temperature is 20 degrees Celsius. So we can find the frequency because we're given the number of beats or oscillations of the mosquito's wings, which is 620 beats. And we know that the time it takes to undergo those beats is 1 second. So 620 beats per 1 second will give me a frequency of 620 hertz. I know that the air temperature is 20 degrees Celsius, and we are trying to find the wavelength. So in order to find the wavelength with the frequency, I know I'm going to need the wave speed. And in order to find the wave speed, I do need to convert my temperature to Kelvin. So to convert from Celsius to Kelvin is, again, a simple thing to do. I simply take my Celsius temperature, add 273 Kelvin to that. So 20 plus 273 will give me a Kelvin temperature of 293 Kelvin. I can then plug that into my wave speed formula because remember, this temperature always has to be in Kelvin. I cannot plug Celsius temperatures into this formula. So my wave speed is going to be 331 meters per second times the square root of 293 Kelvin divided by 273 Kelvin, and that will give me a wave speed of 343 meters per second. So now I have the frequency. I have the wave speed. I can find the wavelength using my wave speed formula, and I know that the wavelength is equal to the speed of the wave divided by the frequency. So 343 meters per second divided by 620 hertz will give me a wavelength of 0.55 meters. Problem 3. You are listening to an outdoor concert on a day when the temperature is 0 degrees Celsius. The sound of a wavelength of 0.490 meters is emitted by a flute on the stage 125 meters from where you are standing. All right, first of all, why are you at an outdoor concert when it's 0 degrees outside? That's crazy. What the heck is wrong with you? Why would you do that? Especially a concert that has a flute in it. I mean, it's not like it's like a good rock concert or something like that. It's like it's a flute. Unless it's like Jethro Tull or something like that. Ask your parents who they are. They might know. All right, enough of that. Let's get back to the problem. What are we given here? We're given the temperature. We know it's 0 degrees outside. We are given the wavelength of the sound emitted by our flute at 0.490 meters. We are given the distance to the stage of 125 meters. And we know at 0 degrees that my wave speed is 331 meters per second. Remember, there are a couple of wave speeds that are kind of common that we use a lot. At 0 degrees Celsius, my wave speed is 331 meters per second. At 20 degrees Celsius, my wave speed is going to be 343 meters per second. That's another common one that we'll see because 20 degrees Celsius is what we commonly refer to as room temperature. So the first part of this problem asks us, what is the time elapsed before you hear the sound emitted from the stage? So we are looking for the time here. So to find the time, we are given the distance of 125 meters. We know at 0 degrees, the wave speed is 331 meters per second. So to solve for time, I simply have to divide the distance by the wave speed, and 125 meters divided by 331 meters per second will give me a time of 0.378 seconds. Part B of problem 3 asks, what is the frequency of the sound? So in this part, we are trying to solve for frequency, and that should be pretty straightforward by now. We know the wave speed is 331 meters per second because it's still 0 degrees outside and you're still at this concert. Go home, get a cup of hot chocolate, go inside, listen to the radio. All right, I'm getting off again. Let's get back to this. All right, so we're looking for the frequency. We know that we have the wave speed and the wavelength. So in order to find the frequency, we just take our wave speed and divide it by our wavelength. So 331 meters per second divided by 0.490 meters will give us a frequency of 676 hertz. Problem number 4. The pulse echo technique is used in diagnostic medical imaging. A short ultrasound pulse is emitted from the device, and the echoes are produced when the pulse is reflected at a tissue interface. The echo signals are received back at the device and then analyzed to build up an image of the organ. Fascinating stuff here. The speed of sound in soft tissue is 1,540 meters per second. Don't ever tell me you never learned anything in physics. You learned the speed of sound in soft tissue. If an echo is received 5.82 times 10 to the minus fifth seconds after the pulse was emitted, how far is the tissue interface from the ultrasound device? So we are given the speed of the sound wave, which is 1,540 meters per second, and the total time it takes for the sound wave to be emitted by the ultrasound device, reflect off the tissue, and return to the ultrasound device is 5.82 times 10 to the minus fifth seconds. And we are being asked to find the distance from the ultrasound device to the tissue. Now remember that the sound wave has to leave the ultrasound device, reflect off the tissue, and then return to the ultrasound device. So if we are trying to solve for the distance here, we need 1/2 of the total time it takes for the sound wave to make the round trip. So 5.82 times 10 to the minus fifth seconds divided by 2 will give us a time, a one-way time, of 2.91 times 10 to the minus fifth seconds. Now to find the distance, I simply have to multiply the speed times the time. So 1,540 meters per second times 2.91 times 10 to the minus fifth seconds will give me a distance of 0.0448 meters or 4.48 centimeters. Problem 5. An echo off a building is heard 8.0 seconds after the sound is created. How far is the building from the observer if the air temperature is 20 degrees Celsius? So we are given the total time it takes for the sound to leave the source, reflect off the building, and return to the source, and that is 8.0 seconds. My temperature is 20 degrees Celsius, and we are trying to find out how far the observer is from the building. I know I'm going to need to know how fast my sound wave is traveling, and in order to do that, I am going to need to have my temperature converted to Kelvin. So let's do that first. I know that my Kelvin temperature is going to equal 20 degrees Celsius plus 273. That is going to give me a temperature of 293 Kelvin. I can now plug that into my wave speed formula to solve for the wave speed. I know that the wave speed is equal to 331 meters per second times the square root of 293 Kelvin divided by 273 Kelvin, and that will give me a wave speed of 343 meters per second. And this is another one of those very common wave speeds for sound, which is at room temperature of 20 degrees Celsius. So now I have my wave speed and I have the time. Now note when I plug my time into my distance formula, distance equals velocity times time, that I need 1/2 of my total value. So I'm only going to plug 4 seconds into there because 8 seconds is the time it takes to make a round trip. And I just need to know the distance between the observer and the building. So I need 1/2 of that time. So 343 meters per second times 4.0 seconds will give me a distance of 1,372 meters.